instead of 10 partitions of 3 levels, which gives you next 30 IOs, you can just go through that one 7-level partition, which is, well, a little bit more efficient. All right, moving past partitioning, optimization versus execution. Note that we actually mentioned this already. Note that we may plan something and not execute it. This is that same one we looked at before. I'm not going to spend the additional time on it. Note that one way of verifying this is to turn on Statistics IO. Here we have Statistics IO turned on. It is telling us that we have IO being performed on the PTTX table. So when it comes time to select the indexes, we review the index types. Well, actually, we're going to do all these. I'm just not going to read them to you because time is a little bit short. The index types we have are clustered, non-clustered, and full text. Full text is beyond scope of this particular talk. Clustered index. We can have up to 1 clustered index per table. Data is maintained in the clustered index order. Note that if we are using the non-all-page locking techniques, it's going to be mostly in order, as opposed to completely in order. We will talk about what happens physically as we start moving into this one. We have up to 248 non-clustered indexes. Why do we have up to 248 non-clustered indexes? Well, one of the things that we're going to find is that the data can only be sorted one way. Because we can only sort the data one way, we're only going to have 1 clustered index. We need a way of accessing the data that's not sorted. So, indexes themselves are balanced B-tree type structures. We have some restrictions on widths of the indexes and the total index entry widths. We can index things like text, image, and bit columns. It's simply not a good idea because we aren't usually going to do much with those. I haven't tried it recently. It does say, though, in the documentation that you can do that. This is the type of thing you might try in a classroom rather than in real life. Indexes are maintained and used internally by the server to improve performance. You probably knew that one already. This is something the application programmer does not usually refer to. If you're forcing indexes, chances are there's some sort of optimizer issue that you haven't come to grips with yet. How does the clustered index work? Here we have a clustered index on last name. If we look at the data pages, we have a set of linked pages which are sorted in order of the last name, which is that last index order. Once again, we'll get into physical structures in just a few minutes. With the clustered index, let's say that we are looking for example for Joe Baker. Baker is, and hopefully you can see my pointer. We start at the root page as the entry. Baker is between Albert and Jones. Because Baker is between Albert and Jones, we follow the Albert pointer up to the intermediate page. We're still looking for Baker. We're on the intermediate page. Baker is between Albert and Brown. We follow Baker down to the data page. Now we're on the data page that we know Baker is on. Why? Because Baker is between Albert and Brown, and this is our data page. We scan the data page. We pick the information up. Depending on some other factors, we may also be using this for something along the lines of a starting point for bringing back all the Bakers. We may end up using this or for a variety of different factors. Let's just stay with this one for a moment. So let's take the clustered example and move down to the non-clustered example. Then we'll come back and we'll compare and contrast a little bit. Non-clustered index mechanism. Well, let's say, just for the sake of argument, that we have a non-clustered index on first name. Sometimes you want to be able to do a lookup in either direction. Well, if you're doing a lookup in one direction versus the other, how do we get there from here? Well, the first part of how do we get there from here is we pick the name. Let's say we're looking for Amy. Starting at the root page, again, it's a B-tree structure, so we're always going to start at the root page. Amy is between Amy and George. We follow the Amy pointer to the intermediate page. Amy is between Amy and Bob. We follow that to the leaf page. Now that we're on the leaf page, what we have is one entry per Amy. Having one entry per Amy means that we can find all the Amy's, pick up all the Amy's. Once we've got that, what we're going to do is we're going to make a separate page request. For each of the Amy's there at the leaf page, we're going to request the data page that Amy resides on. Here we have 2 Amy's. We're going to make 2 page requests. Now things start to get interesting. we're going to compare and contrast the clustered versus the non-clustered a little bit. As we're looking for the clustered versus the non-clustered, one of the first things that we spot is that in the non-clustered, if we're going to pick up multiple Amy's, we need multiple entries. Coming back to the clustered index, what if we have 2 or 3 Joe Bakers, or 2 or 3 Bakers? Well, when we're looking for the Bakers, one of the things that we find is that if we had 3 Bakers on this page, we might pick all 3 Bakers up without any additional work. So 1, 2, 3 IOs, suddenly we've got 3 Bakers. Now, let's take a look at that non-clustered index. And let's say, just for the sake of argument, that we are going after 3 Amy's. Well, now we have 1 IO at the root page, 1 at the intermediate page, 1 at the leaf page. We've got the 3 IOs same as we had on the other, but now we need to make 3 page requests. Now, they may be logical page requests, they may be physical page requests, but they are still page requests nonetheless. So what happens there? We find that based on bringing multiple rows back, we are frequently in a situation where a non-clustered index is going to cause a bigger performance hit than a non-clustered index. This is pretty common. One of the things you'll frequently find is that when you have a non-clustered index, the server is going to ignore it and do a table scan. Why would it do that? Well, just for the sake of argument, let's say that we have 1,000,000 data pages at 100 rows per page. With 1,000,000 data pages and 100 rows per page, we have about 10,000 pages of data. Well, let's say there's 20,000 Amy's. Well, to do a table scan, it costs me 10,000 page requests. But to bring back 20,000 Amy's, with the non-clustered index, I have 20,000 page requests, plus I also have to go through the leaf pages and go through the index structures to pick all that information up. Tends to be a lot more expensive. So when we choose indexes, when we make the decision as to how we're going after the data, when we start doing this as part of what we're doing in the optimization process, one of the things that happens is the optimizer is going to estimate how many page reads it's going to cost to perform any particular type of activity. This is simply part of the optimization process. Let's think about this from another perspective as well. What happens if we are choosing an index? Well, when we're choosing an index, one of the things we'll look for is the type of activity we're going to get when we are going after the data. Let's say we're looking for last names. Do I have a customer service rep doing a last name lookup? Well, if that's going on, then I may want to cluster by last name. What if I don't look at things that way? What I'm usually doing is looking for customers by region. Give me all the customers in Chicago. Well, in that case, what you may want to do instead is, instead of getting all the the Chicago-related customers by name, let's go ahead and cluster by city. That gives you a great benefit, because what that enables you to do is just bring them all up by walking the page chain instead of picking things up separately. So clustered versus non-clustered. The clustered index structures tend to be 1 IO narrower than the other structures, and the reason it tends to be 1 IO narrower is that the clustered indexes have fewer entries. We have an entry per page rather than an entry per row. And what that does for us is just simply make these structures a lot smaller. Clustered indexes are great for ranges of data. Note that this makes it ideal for things like foreign keys. So if I'm going after header detail rows, frequently a very good idea to say, okay, give me all of the detail rows for this header. Well, guess what? we're always going after the detail rows by that header. Because we're going after the detail rows by the header, what we're going to need to be able to do is pick those detail rows up